In this video, we will be working through some multiple choice questions and different types of FRQs as well for your response questions that involve change in concavity and points of inflection and intervals of concavity. If you haven't watched my first two videos on 5.6 and you don't know how to find points of inflection, or you don't know what a point of inflection is, or you don't know when a function is concave up or concave down, I would highly recommend that you watch those before watching this one. On the open interval from 0 to 1.2, the graph of the function g of x equals the tangent of x cubed minus 5x to the fourth minus 3x plus the natural log of x changes concavity at which value of x? Changes concavity simply means that we have a point of inflection there. And points of inflection occur when the second derivative changes signs. So first what I'm going to do, I'm going to hit the y equals button, and in this slot for y1, I'm going to input my original function. Now in the slot for y2, I'm going to put in the derivative of y1. So hit the math button and then the 8 to get d dx, put the x in, and then to get d dx of y1, hit vars, scroll over to y vars, hit function, and then the function that you want to put in is y1 for all x, so x equals x. But then for this third one, because I'm not looking for the first derivative, I need information about the second derivative. So I'm going to take the derivative of y2, derivative of the derivative. So again, hit math, 8, d dx, and then put in vars, y vars, a function, but then scroll down to y2 because that's the function that you want. So it's taking d dx of y2 at all x, so for all x. Now at this point, the only function that I want to actually show up on my graph is the y3 one. So I'm going to go up to the y2, unselect the equal sign there, go up to y1, unselect the equal sign there, and lastly, I'm going to change my window. I'm only looking on the open interval from 0 to 1.2. So I hit window and then change the x-min to 0, the x-max to 1.2, hit enter, and then graph. Now I'm looking at my graph of the second derivative here, and I know that the function changes concavity or has points of inflection when the second derivative changes signs. So right at that point right there, the second derivative is changing signs from negative to positive. So I just need to find what is that point. So I will hit second trace to get up to calc, and then I want it to calculate the 0. And then I will scoot the left bound. I will scoot the little cursor to the left of this 0. And right now it's to the left, hit enter, and then scoot it to the right, hit enter one more time, and then it will give you the value of the 0. It says the value of the 0 is 0.9537, or 0.954 if you round. So this is where the original function g changes concavity on this specific interval. I do have a video with more examples of graphing calculator problems if you want to practice more of those. Let f be a function with the second derivative f double prime of x equals x minus 3 squared times x plus 2 times x minus 7.5. What are the x coordinates of the points of inflection of the graph of f? And then we have a whole bunch of options to pick down here. These are the options that they give us, and then we have choices with the specific options. So they have already found the second derivative for us, so we don't need to worry about that. Now what we need to do is find the potential points of inflection. So which values of x can we plug in that are either going to make f double prime of x undefined or equal to 0? There aren't any that we can plug in that are going to make f double prime of x undefined, but we can start a list of potential points of inflection that will make f double prime of x equal to 0. So now we can set each of these terms equal to 0. X minus 3 is equal to 0. That means that x could equal 3. X plus 2 is equal to 0. That means that x equals negative 2. X minus 7.5 is equal to 0. That means that x equals 7.5. These are our potential points of inflection. Remember, they are not guaranteed until we verify on a sign chart that these are actually points where the second derivative does change sign. So now I'm going to make that sign chart. So first, I will test f double prime of negative 3 for this window right here. This is going to wind up being positive because these two negatives cancel. Now I will find f double prime of 0. This will wind up being a negative value. Then I will find f double prime of 4. This will wind up being a negative value. Then I will find f double prime of 8. This will wind up being a positive value. So now I can see that x equals 3 is actually not going to be a point of inflection because f double prime of x does not change signs. However, x equals -2 will be a point of inflection because f double prime of x does change signs. So yes, x equals -2, no, x equals 3, and yes for x equals 7.5 because f double prime of x changes signs. This means that choice D is the correct answer because 1 and 3 only are the points where we have points of inflection. Let f be the function given by f of x equals e to the x times 5x. The graph of f is concave down when, and then we have these intervals. So first step is to identify the domain of the function. The domain of f in this case is going to be all real numbers because you can plug in anything that you want for x. Now we need to find f double prime of x, so we will have to use the product rule twice. Now there's a little bit of a shortcut here because when we're taking the second derivative, we have to find the derivative of 5e to the x, which is 5e to the x, plus the derivative of e to the x times 5x. We know what that is. We just found that. That's f prime of x. So the derivative of e to the x 5x is going to be this. So we can just recopy this. So it's 5e to the power of x plus e to the x times 5x. So that entire thing is our second derivative. If you wanted to, you could also just use the product rule there and you would get the same exact answer. So now I'm getting that f double prime of x equals 10e to the x plus 5x times e to the x. What I'm going to do is first think about, are there any values of x that I can plug in that will make f double prime of x undefined? And the answer here is no. However, I can set f double prime of x equal to 0 to find potential points of inflection. So 10e to the power of x plus 5x times e to the x is equal to 0. Now I can pull out a greatest common factor of 5e to the x. At this point, I can set each of these equal to 0. If I set 5e to the x equal to 0, then divide both sides by 5, I get that e to the x is equal to 0. But when I try to apply the natural log to both sides to cancel out the e, I get natural log of 0 on one side, and that does not exist. So I'm just going to make a little note there that says does not exist, and then I can stop that side. However, I still have this to do, so 2 plus x is equal to 0. And when I set 2 plus x equal to 0, I get that x is equal to -2. That is a potential point of inflection. Now I can make my sign chart. First, I will test f double prime of -3 to test in this window. And when you're finding f double prime of -3, that's going to be 5 times e to the power of -3 times 2 minus 3. To find 5e to the power of -3, you can rewrite this as 5 over e to the power of 3. That's going to be a positive number. So f double prime of -3 will be a positive number times a negative number, which will be a negative number. So negative goes on the sign chart right there. Then I will test f double prime of 0. This is 5 times 2, or 10, which is a positive number. This means that f is concave down on the open interval from -infinity to -2, or when x is less than -2. So answer choice A, because this is where f double prime of x is less than 0. Let h be a function defined for all x not equaling 0 such that h of 4 equals -3 and the derivative of h is given by h prime of x equals x squared minus 2 over x for all x not equaling 0. On what intervals, if any, is the graph of h concave up? Justify your answer. So the first thing is that they gave me my domain. It's all x except x equaling 0. Now to find h double prime of x, I will use the quotient rule. H double prime of x equals x squared plus 2 over x squared. Now I will find my potential points of inflection. So I need to determine which values of x can I plug in that will make h double prime of x equal to 0 or undefined. Well, it will be undefined if I plug in x equaling 0 because then I'll be dividing by 0. However, that one is not within my domain, so I cannot use that as a potential point of inflection. If I set my numerator equal to 0, I would be making h double prime of x equal to 0. So that's what I'm going to do. I'm going to say x squared plus 2 is equal to 0. This gets me x squared equals -2. But then if I take the square root of both sides, what I'm getting is that x is equal to plus or minus the square root of -2, which does not exist because you can't take the square root of a negative number. This means that I have no points of inflection. I only have a domain issue. So when I go to make my sign chart, what I'm going to have is I'm just going to have it going from -infinity to infinity, and this is my sign chart for h double prime, and then I'm going to have that one domain issue, 0, on my sign chart. Now I will find h double prime of -1. H double prime of -1 will be -1 squared, which is 1, plus 2 over negative 1 squared, which is 1. So 3 over 1, which is a positive number. Then I will find h double prime of 1, which is 1 squared, 1 plus 2, so 3 over 1 squared, which is 1, which is also a positive number. This means that since h double prime of x is always greater than 0, the graph of h is concave up for all x not equaling 0. H double prime of x is greater than 0 for all x not equaling 0. Therefore, h is concave up for all x not equaling 0. A cubic polynomial function f is defined by f of x equals 4x cubed plus ax squared plus bx plus k, where a, b, and k are constants. The function f has a local minimum at x equals negative 1, and the graph of f has a point of inflection at x equals negative 2. Find the values of a and b. Well, the first step is to take the first derivative and then the second derivative. So I'm first going to find f prime of x. F prime of x will be equal to 12x squared plus, and then this one is a little weird, but we're going to follow the same rules, plus 2ax plus b. Now, since I know that f has a local minimum at x equals negative 1, and I know that all relative extrema, or local extrema, occur at critical numbers, I know that x equals negative 1 must be a critical number. This means that f prime of negative 1 must be equal to 0. So 0 must be equal to 12, and then I'm going to plug in negative 1 for x. Negative 1 squared plus 2a times negative 1 plus b. That will get me 0 is equal to 12 minus 2a plus b. And I can't solve that until I have some more information about the variables. Now I'm going to take f double prime of x to get the second derivative so that I can deal with this point of inflection. F double prime of x is equal to 24x plus 2a, because 2a is my coefficient, and b goes away because that's just a constant. Now, I know that f has a point of inflection at x equals negative 2, so f double prime of x must be equal to 0 at x equals negative 2. This means that f double prime of negative 2 must be equal to 0. So now I will go through and plug negative 2 in for x into my f double prime function. So 0 needs to equal negative 48 plus 2a. This means that a needs to equal 24. Now I have enough information to go back to my other equation, so I will bring it down here, and I will say 0 is equal to 12 minus 2 times a. 2 times a would be 48. 12 minus 48 plus b. So 0 is equal to negative 36 plus b. This means that b is equal to 36. And since it did not ask me to justify or explain, I can just leave it as this. A equals 24 and b equals 36. Consider the curve given by g of x equals the natural log of 9x times x over 6. Does the line tangent to the graph of g of x at x equals 2 lie above or below the graph of g? Explain. Here we are going to need to deal with concavity, because the only way to tell whether the line tangent to the graph lies above or below is to determine whether g is concave up or concave down at x equals 2. If g is concave up at x equals 2, that means that the tangent line will lie below the graph. If g is concave down at x equals 2, this means that the tangent line will lie above the graph. So in order to determine the concavity, we have to find the second derivative first. So we're going to go through that same process of first identifying the domain, which in this case is all real numbers because you can plug in anything you want. And then we're going to find the second derivative. G double prime of x is 1 over 6x. So normally at this point I would go find the points of inflection, but I actually don't care about the points of inflection in this specific situation because I am only looking for, is the graph of g of x concave up or concave down at x equals 2? So in order to find that, what I can do is I can plug in 2 to my g double prime function, find g double prime of 2. This is 1/12, which is a positive number that's greater than 0. So I will say the line tangent to g at x equals 2 lies below the graph of g because g double prime of 2 is greater than 0. So g is concave up at x equals 2, so the tangent line lies below the curve. There is my full explanation. If you want more practice with free response questions, you can find some more examples in my 5.6 video part 1.